All right, so this help video is designed to give you 3 different ways to do limiting reactant stoichiometry so that you can decide which way you like best. So if you're here for help, then I'll try to put the table of contents in the beginning of the ed puzzle so that you know where you can skip to if you'd like, but we're going to do this 3 different ways, the same problem. And then you'll have an opportunity to try another problem yourself. So, limiting reactant stoichiometry, one way to do this is to use both reactants to find the theoretical yield. So I'm going to do this way first, and then we'll come back and go from there. Once you know who's limiting, then of course this question wants to know who's in excess and how many grams of each remain. This question is like a question on steroids because it has 3 reactants. Okay, so this is very unusual, but it's going to give you some really good practice. So if you want to try this on your own, using both reactants to find the theoretical yield, you can, or you can skip ahead to a different way if you'd like. So they did not give us the equation for this. They tell us that we're going to prepare sodium nitrite by reacting nitrogen monoxide and oxygen with sodium carbonate in solution, and that also we get carbon dioxide. So I wrote the equation, and I discovered, it was a little bit difficult to balance, but I discovered that I have 4 NO and 1 O2 and 2 Na2CO3s reacting to form 4 Na and O2s, sodium nitrites, and 2 CO2s. So my equation will remain the same for all ways that I do this. And I actually don't really like it like that, but I'm going to leave it there. So let's start by finding how much we could yield from all of our reactants separately. So I'm going to start with 154 grams of Na2CO3. I'm going to convert that to moles. And then I'm going to go from moles of that to moles of the product they asked me about, which would be NaNO3. And technically, I could stop there if I wanted to and find which one gives me the fewest number of moles and then go on to figure out the grams from that. But since it's always the same last thing, I'm just going to go ahead and go on to grams, which is what they asked me about. Sorry, NaNO2, not NaNO3. So when I do this from the periodic table, sodium carbonate is 105.99 grams and sodium nitrate is 69 grams, and my mole ratio is 4 NaNO2s to 2 Na2CO3s. I figure this out and discover that this could give me 200.50 grams of NaNO2. I'm not done though, I'm not worried about sig figs yet. I'm going to do the same thing with my 105 grams of NO. Grams of NO to moles. Moles of NO to moles of NaNO2. And moles of NaNO2 to grams. I already know that, 69 to 1. Moles of NO, 1 mole is 30.01 grams from the periodic table. And from my equation, this is 4 to 4. This gives me a potential of 241.42 grams of NaNO2. And since using all of the sodium carbonate would produce only 200 grams, I already know that this is impossible. I'm going to do it once more. 75.0 grams of O2. Let's see how much of the NaNO2 we could produce from that. Grams of O2 to 1 mole of O2, that's going to be 32. And moles of O2 to moles of NaNO2 from my equation, 1 O2 to 4. And then back out again from moles, 1 mole of NaNO2 to grams of NaNO2, and that's the 69 grams, which would allow me to produce 646.88 grams of NaNO2, which is definitely way more than if I used all of my sodium carbonate, so this is also impossible. So my theoretical yield comes from this 200.50, which means that with 3 significant figures, this would be 200.50. grams of NaNO2 as my theoretical yield, as my answer to this part. So this also tells me now that the limiting reactant is the Na2CO3, which makes the excess reactants the NO and the O2. And they want to know how much of each of those is left. So in order to do that, I have to figure out how much of each of those I used, which I'm going to do from my limiting reactant. So I'm going to say 154 grams, and this gets really cumbersome. I'm going to go grams to moles of Na2CO3, and I'm trying to figure out how much NO I'm going to use. So this is moles of Na2CO3 to moles of NO from my equation, 4 NOs to 2 Na2CO3s. And then back to grams, because I'm going to have to be able to subtract to find out how much is left. So 1 mole of NO is 30.01 grams of NO, which means that I found that I've used 87.207 grams of NO, and the NO left will equal what I started with minus what I used, which would be 105 grams minus 87.207 grams, which is 17.792. And I'm going to round to the whole number because my given was to a whole number, which is 18 grams of NO left. All right. I would have to do the same thing from my limiting reactant to O2. And so this process works the same way. I'm going to do it for you, but it's kind of cumbersome. 75 grams of O2, grams of O2 to moles, moles of O2 to moles. Oh, sorry, I did this wrong. Start over. I'm going to take my limiting reactant, 154 grams of Na2CO3, and convert that to how many grams of O2 were used. Sorry. So I'm going to go to moles of sodium carbonate, then moles of sodium carbonate to moles of O2 from the equation. This is 1 O2 to 2 sodium carbonates, then 1 mole of O2 to 32 grams. Tells me that I used 23.2474 grams used. So O2 left equals the O2 to start minus used, which is starting, there's my 75 grams, minus the used, which was 23.2474, which then gives me 51.7525. I'm going to round this to the tenths place now because that's what I have from my given, which would be 51.8 grams of O2 left. So this is one way to answer all of their questions. This is using both reactants to figure out which one's limiting, and then using the limiting reactant to go from there. So that's one way. Let's switch. Now we're going to do it the compare the have and the need way. Okay? So I'm going to actually take a shortcut here and say if we started with the Na2CO3, we would do our 154 grams of Na2CO3, and we need to figure out grams of O2, and we need to figure out grams of NO that we would need to go with it. Okay, so I already have that math up here. I'm not going to make you look at all this math again, but I already have that math up here. This grams of O2 that I used and this grams of NO that I used are the amount that I would need. Okay, so let's come down here and talk about how you do that comparison. The grams of O2 that I would need would be 23.2 grams. And the grams of O2 that I have is 75 grams. And so I have way more than I need, so O2 is not limiting. Okay, I'm going to do the same thing. The grams of NO that I need from the calculation that we did up here was 87.2. 87.2 grams, and the NO that I have is 105 grams, which means I have more than I need, and so NO is not a limiting reactant. So this tells me, since neither of those is limiting, that the Na2CO3 is the limiting. The other two are excess, and then to do the how much is left over, I would have to come back and subtract, because at this point I already know the amount that I used. So at this point, if I have already done that, it saves me a little bit of trouble later. All I have left to do is this step to tell you how much is left, and this step to tell you how much is left. Okay, so that actually saves you a little bit of time if you get lucky and you pick the right one to start with. That would be luck. Okay, all right, or there's the third way, and this would be using your BCA chart and working it pretty much in moles. So if this is what I'm going to do, I'm going to actually go ahead and find given moles of everybody. So I'm going to stop at moles. I'm going to take my 154 grams of Na2CO3, 105.99 grams in 1 mole, and this comes out to 3.5. Sorry, no. I've got to find my right numbers. This comes out to 1.45 moles of Na2CO3 to start. And I'm going to do the same thing with my 105 grams of NO, 30.01 grams of NO to 1 mole. Gives me there's my 3.5 moles of NO to start. And I'm going to do the same thing with the 75 grams of O2. 1 mole of O2 is 32 grams, and this is going to give me 2.34 moles of O2 to start. And I'm going to do a BCA chart. So I'm going to rewrite my equation as, make it really big here, 4NO plus O2 plus 2 Na2CO3 yields 4 NaNO2 and 2 CO2. Okay, so my BCA has to be in moles, and I'm going to plug in the moles that I just discovered. So for the NO, this was 3.5. For the O2, this was 2.34. And for the sodium carbonate, it was 1.45. And I don't really care about the carbon dioxide because they never asked me, but I had no sodium nitrate to start and no carbon dioxide. Now I can do this in little baby steps to figure out who's limiting. I might be able to do this in my head. And if that's the case, I'm actually going to start with the O2 because its coefficient is 1. And I'm going to say, if I were going to use all of my O2, I would need twice as much sodium carbonate. So twice as much sodium carbonate, 2 times 2.34 is 4.68, right? And I don't have that much. So if I were going to come in here and do minus 4.68, that would give me a negative number, which tells me that the oxygen is not limiting. All right, so I'm going to make myself a note, not the limiting. And I'm going to maybe go from the sodium carbonate at that point because I know I did not have enough sodium carbonate. Also, I can look at this and say the sodium carbonate is 2 to 4. I would need twice as much nitrogen monoxide. And so if I have twice as much as 1.45, that's 2.9. And if I subtract 2.9 here, that's a positive number. So what this tells me is that the sodium carbonate is limiting, and these two are the excess, the nitrogen monoxide and the oxygen. So now I can say I'm going to use all 1.45 of the sodium carbonate. I'm going to use 2.9 because I just figured that out of the nitrogen monoxide. And so that gives me 0.60 moles left. And to figure out how much oxygen get used, I might need to do a small little stoichiometry step. So I'm going to say I'm using all of my 1.45 moles of Na2CO3. And in the equation, this is 2 moles of Na2CO3 for every 1 mole of O2, which means 1.45 divided by 2 is 0.725 moles of O2 needed. So this is going to be minus 0.725. And after I do that, that gives me 1.615 moles of oxygen left. So I can already answer in moles how much is left, which means this is really quick now because this is just going to be a quick conversion from moles to grams. 1 mole is 30.01 grams of NO, which comes out to 18 grams. And NO left. And I can do it again for the oxygen. This is in moles, so 1 mole is 32 grams of oxygen, which gives me 51.68 or 51.7 grams of O2 left, and no Na2CO3 left. And then they also asked me how many moles and grams of, or how many grams of Na2NO3 I could form. Notice that if this is my limiting reactant, it's twice as much formed. It's also the same as this. So this is really easy. If that used 2.9 moles, then this is going to add 2.9 moles, which gives me 2.9 moles. And I can convert that to grams really quickly of Na2NO3 at 69 grams per mole, and that tells me 200.1 or 200 with a decimal grams of NaNO2 formed, right? So I can answer all of their questions using my BCA chart. And notice that I get pretty much the same answers. There's a few differences just from a little bit of rounding, but I get pretty much the same answers as I did up above. So you may discover that you actually like this thought process better, that it makes more sense to you to do them little bits at a time than to do great big long stoichiometry problems. I would encourage you to try it. So to do that, I've given you one more problem. And you'll need to write and balance the equation, and you'll need to copy it into wherever you're putting this. But then I would like you to stop the video and try on your own. This is a lot easier for several reasons. There's only 2 reactants. The equation is really easy to balance, all of those things. And so I definitely want you to try it yourself, come back and see how you did. Stop the video here. Okay, so I'm going to write the equation of hydroiodic acid and hydrogen carbonate or bicarbonate, forming potassium iodide, water, and carbon dioxide. You should have been able to do this by yourself. This is a double replacement that forms H2CO3, which then decomposes into H2O and CO2. So just be aware of that. Hopefully that was comfortable for you, even though I didn't tell you that you also got water, or it did tell you. Hopefully you could have done it on your own. I'm going to do this in the BCA chart because I really like this. This is already balanced, which means everything's in 1-to-1, and it makes it really, really, really easy. Okay, so the first thing that I need to do is take my grams of this and find moles so that I can put it in my chart. Remember, this has to be in moles. Okay, so 398 grams of HI. HI's molar mass is 127.91 grams, which gives me 3.11 moles of HI. I'm going to put that in my start. I also have 318 grams of KHCO3, so 318 grams. The molar mass is 100.12 in 1 mole, which gives me 3.18 moles of KHCO3. So because these are 1-to-1, this becomes really easy. I also have none of my products, and this becomes really easy because for every 1 HI, I have to use 1 KHCO3 and vice versa. So because they're 1-to-1, you can see that you're going to run out of HI first. So I'm going to use it all, and I'm going to use the exact same amount of the KHCO3, and I'm going to form the exact same amount of all of my products because they all have coefficients that are the same. So now there's no HI left. There's 0.07 moles of KHCO3 left. And there's 3.11 moles of Ki formed, which is the other part of the question that they asked me. All right, so now this becomes super easy because I can take 0.07 moles of KHCO3, convert it back to grams using the 100.12 grams per mole, and I have 7.01 or 7.0084. Technically, this is only 1 sig fig. I don't particularly much like that, but we would say 7 grams of KHCO3 left. And to figure out how many moles of Ki are formed, I'm going to use the molar mass. 1 mole of Ki from the periodic table is 166 grams, which is 516.26, or with 3 significant figures, equals 516 grams of Ki formed. And using my BCA chart, because they were 1 to 1 to 1, it was super fast, and I'm done with the whole question. So hopefully you were successful. Hopefully this was helpful. I think this will probably be one of the more challenging things at the start of the year for you, so make sure you work really hard at the